Hey everybody, in this next video lesson, we're going to talk about a topic called heat of solution. Now in the last video lesson, I introduced to you the concept of a thermochemical equation. Those are chemical reactions that have heat as either a product when it's exothermic or as a reactant when it's endothermic. And those were chemical processes. But there are some physical processes, specifically dissolving, that could also have an energy change associated with it. And this is called heat of solution. Now, the symbol for heat of solution is a delta H with a subscript S for solution. And this is the heat required or released when a substance dissolves into water. You see, the ionic bond that holds the crystal lattice together for ionic substances is basically a bond that can be broken or a bond that can be made. And when the bonds are broken or the bonds are made, just like any other bonds broken or bonds made, that can result in an energy change. And so sometimes, like this first example, calcium chloride solid, when dissolved into water, releases 81.74 kilojoules of energy. Now this is a hot pack. Now this is not the chemical hot pack because that's not a chemical reaction. This is just a physical change. Now we can also have cold packs that are behaving the same way. These are different than the cold packs we showed you in the thermochemical reaction video because those cold packs result from the endothermic energy of something that's reacting. This is not a chemical reaction. But if you just take the ammonium nitrate and dissolve it, it becomes ammonium ions and nitrate ions, it actually absorbs 25.7 kilojoules of energy. It's not as much energy that gets absorbed when the ammonium nitrate reacts with the barium hydroxide, which we saw in the last video. This number was much larger. It is a value, although smaller, that can be used to make another type of cold pack. These are just hot packs and cold packs that result from dissolving. A little bit of a side note here though, hand warmers that you use when you're maybe sitting outside on a cold winter's day or you're sitting in a deer stand or whatever, those are actually mainly a solid that is oxidizing, usually iron, and so that's a chemical reaction. Those are chemical hand warmers. This is a physical hand warmer. And also the same principle applies to those self-heating meals, those MREs, meals ready to eat, where basically you're taking magnesium metal and oxidizing, and that reaction releases a lot more energy, so those heat up much faster. But it's just a single displacement reaction that is causing the magnesium and oxygen to produce aluminum metal, and that is also another way to generate heat. So these are examples that you might be familiar with, but these are chemical situations. But heats of solution is simply dissolving. That's a physical change. Now it's nice, and this is a spoiler because we're about to see, but the math is no different than that of a thermochemical reaction stoichiometry problem. You treat it the same way. You take the reaction with its energy and determine how much energy is released when a certain amount is dissolved. Take a look at this next example. Consider the same reaction that we just looked at, the calcium chloride dissolving to make calcium ions and 2 chloride ions. This reaction releases 81.74 kilojoules of energy. So you will make 7.77 grams of Cl ions. What is the energy change that would you expect for this reaction? So in order to solve this problem, we need to set up the stoichiometry, and we need to start with the 7.77 grams of Cl1- ions. And the first step, just like in the last video, was to convert from grams to moles using the molar mass. So 1 mole on top and 35.45 grams of Cl on the bottom. Remember, the molar mass of an ion is the same as the molar mass of an atom. It just has more or less electrons, but the mass is essentially the same. So this gets us to moles of Cl ions. Now we need to use the thermochemical reaction and specifically the mole ratio of the chloride ions to the energy. So we want to put 2 moles of Cl1- on the bottom and 81.74 kilojoules on top. But remember, since this is a product, that this energy is released, and so we want to put a negative out in front of the 81.74 kilojoules. Now I punch this into my calculator, and I get a final answer of negative 8.96 kilojoules of energy, or you could say 8.96 kilojoules of energy released. But you shouldn't say negative energy released, because that would be essentially a double negative. So that's how you do a problem. And as you can see, it's very similar to the thermochemical equations that we did in the last one. Now I want you to pause the video and try this next one, and I will then work out the answer and see if you got it right. All right, I start with the 15 joules of energy, and I want to convert from joules to kilojoules, so I divide by 1,000. because my energy up in the thermochemical reaction, or the heat of solution, is in kilojoules. So now I want to convert kilojoules to moles of what I'm looking for. I'm looking for grams of NH4NO3, so I've got to go to moles of NH4NO3 before I can convert to grams. Final step is convert to grams using the molar mass. That's N plus 4 H's plus 3 O's. And once I set all this up and do the math, you should get an answer of 4.7 grams. That's rounded to two significant figures because the original number, 1500 joules, is only 2 sig figs. Well, that takes care of this video lesson on how to do calculations involving heat of solution. Thanks for watching.